to this week 3 tutorial for our statistic and analysis. So we're going to going through you with the tutorial questions and some of the R code demo. Okay. So first thing, I'm going to share my screen. Okay. So first, please go to the course NTU module. So we go to the content, make sure you're in the content. After you're in the content, we can download a few things first. So these are our data set that is being used for our demo code and our tutorial code. So you download these two first. Then you scroll it down. You should be able to see the week 3's complementary content by now. So you download this week 3 R demo, random variable and probability distribution, the R. You also download the R solutions 3, week 3 R. So now I have these 4 items being downloaded. So let's have a look. Make sure you have these 4 downloaded. So in my download folder, you can see there's 4. So first thing is unzip these 2 data files. So you open it, you will see a few CSV files for R demo. So these are the CSV file that will be used during the R demo and those data set being used in your video tutorial, in your video lectures. For the data set for R tutorial, so some of the R tutorial from week 5, week 7, and week 10, it requires you to use some data set. So I have curated and all placed here. So what you can do next is you can place your all the R demo script, including week 1 to week 12, into your data set for R demo, and the tutorial R solutions to the data set for R tutorial. The reason for this is when you execute the commands code in the R demo script, it will refer, look for the data set somewhere here. Okay, so it's best to place them together. So now next is you open your RStudio. Open your RStudio. Open your RStudio. Let me close it first. Let's start from fresh. So open your RStudio. Once you open it, you will see interactive console like this. So we can type a few things like A equals to 1, then display A, then show you A. So say A equals to a vector 1, 2, 3, 4, 5. Then display A, then A will be a vector. So it's also shown here. Okay. So now I'm going to want to open the R script file. So we are going to open 2 R script file. First is the one on download, R demo. So R demo, we open this R demo. Also want to open another one, which is go up 1 level on R demo, but the R tutorial. Okay, I open these 2. Okay, so let's first start with this week 3 R demo, random variable and probability distribution. So watch your video lecture first. Then there is an example on week 3 slide regarding the Bernoulli and the binomial example. So this is the example shown here. I'll let you have a look. So this is an example. So you are about to flip a fair coin 100 times. So the size is 100 times. You want to know the probability of observing a certain number of heads, let the total number of heads being a random variable x. Then x follows a binomial distribution. To calculate fx, use the binom x and p. X is the value of the x, which is 40. Then n is the size of 100, and the p, the probability of b is 0.5. Okay, fx, small f, is the probability mass function for discrete random variable. Then the uppercase fx is the cumulative probability, cumulative distribution function, cumulative distribution function. So for any f value, so for any x value, as long as it's less or equal to 40, I want to find all their combined probability and sum them together. Okay, so we can use R code to work on this. The first thing is you have a question mark, D by norm, then enter. You do not need a parenthesis here. You do not need a parenthesis here, but if you add, there's no big problem. So normally you do not need. So on here, you will see a help window. It says binomial distribution description. Then so 1, 2, 3, 4. There is a D binom, P binom, Q binom, and R binom. So these are some of the main functions. So the first one is the density, or for discrete random variable, it is the probability mass function. Then the second one, P norm, we call it distribution function. It is a cumulative distribution function, which is a CDF function. Then the quantile function, we'll look at that later. And the random generator. So R means random. So we generate a random variable which follows a binomial distribution of n size and probability. N is how many numbers do you want? Give me one moment, please. 现在先不用，现在不用。不用。Sorry, there is a disturbance here in my office. Yeah, just now we're talking about R for getting n number of random variables. So let's look at here. In our example, we want to find F40, right? So it's a probability mass function. So D norm or D by norm. When you are seeing this autocomplete, right? So I'm just typing it. So I can press tab key, the tab key on the keyboard, it will autocomplete. Then after that, it's showing you the X size probability, mu is the mean value, log equal to false. So to have a complete line of code, you can type X equal to how much? X equal to 40. So 40. X equal to 40. So getting 40 heads. So X is getting 40 heads. And how many coins have you flipped? The total number of trials experiment is 100. 100. Right? 100. Then next is press tab again. So you can use arrow key to select probability equals to 0.5. It's a fair coin. Okay, you run it. Control Enter. So you move your cursor to this line. Control Enter, or you can highlight this line. Say code. Execute. Run select lines. Run select line. So it will give you this value. X equal to 40, size 100, and the probability. D by norm. All right, there is a typo there. So 0.0108. So this is the value that you see from here as well. Okay, now. So to simplify it, you can just place X equal to 40, then 100 is the size by the position. So you get the same result. Next is the cumulative distribution function, P by norm. Okay, it says Q. You notice that is a Q, that is a size, that's a probability, right? Q equals to 40. Then size type tab, size equal to 100, and the probability is 0.5. You run it. It give you 0.028. This is the value that you obtain from here. These are all the X value from 0 up to 40. What is their combined probability from 0 to 40? 0 to 40. Then next is for our habit, we can, for our convenience, we define a probability, the size, and the X value to be 40. So now next is we can calculate you can see the three values here. So I want to calculate F39, then probability binom, variable X value is this value. I should get this value. X, N, and P. And put it 0.0176. So this is F39. Cumulated CDF now 0.006. Then what I see next is the probability to get exactly 40 heads is equals to the big F40 minus the big F39. So you will get the probability of F40. You run it. It says whether this value is equal to that value. Smaller f p norm, p by norm, p by norm. Just better I write it for you. 40, 100, 0.5. What is this? This is minus p by norm, 39, 100, 0.5. You get 0.0189. Then let's calculate the F40. This is then we calculate the F40. Small F40 is D by norm. 40, 100, 0.5. This is your small fx. You see that two values are the same, right? It looks the same, exactly the same. Then now what we are saying that we put a equal sign there. We want to check whether these two are equal. They say it is false. Why is it false? Although the two values are the same. So there is reason somewhere here. It says it's because the floating point, the precision errors in the R calculating engines. So for you to avoid these kind of problems, you can use a called all equal function, just for information, just for all equal function. Then there'll be commas inside these parentheses. So one part you put these small fx, the norm here. Then the other part is the bigger F40 minus the big F39. You run it, it sets true. Okay, so this is one that I want to show you about the CDF and PMF for discrete random variable. Then I have some exercise here for at most 6. So this is for you to run through it for the e-learning quiz. So I've been showing there. And next is a Poisson distribution. It's a website on average is visited by 30 browsers per minute. So let's have a look at this example in the Poisson example. This one. A website on average is visited by 20 browsers per minute. We can use a Poisson random variable to calculate the probability of the number of arrivals. Assume X to be a Poisson random variable, then calculate the P X greater than 25 is equal to 1 minus probability of X less or equal to 25 is equal to P Poisson 25, 20. 25 customers with a lambda rate of 20 browsers per minute. So let's have a look at this one. So this is the example here. So assume X to be a Poisson random variable. So analysis first, we use the CDF. So first, you type a question mark PPO. Let's run it. So Poisson distribution. Now, so again, you have the D poise, P poise, Q poise, and R poise. So for general order distribution functions, you have the D, P, Q, R. So for the density, or called the probability mass function, it is X number of visitors, lambda is number of browsers, visitors per minute, then these two values, right? So our question is saying that P plus 25, comma 20 is less or equal to 25 visitors per minute. So this is a CDF, cumulative density function, So it includes 0 browser, 1 browser, 3 browser, 4 browser, and so on, up to 25 browsers. What is the combined probability? So this is one unused argument. Sorry, not X, Q. 0.887815. Okay, so this should be the same. No, it's not here. Then it says more than 25 minutes, more than 25 visitors. So you should use 1 minus it or 1 minus it. 1 minus this, you get 0.11, 12% chance, 12% chance, 12% chance. Okay, then discrete random variable exercise is for you to browse it. Display the result. Okay, next you will look at a continuous random variable. Continuous random variable, the example that we're using here is the normal distribution. It's a normal distribution and the uniform distribution. So here is a normal distribution, Gaussian distribution, bell curve. Fx must be non-negative for any x. Fx, bigger Fx is the non-decreasing x and will be approaching 1 when x approaching positive infinite. R command for random variables. So we are creating a F1. That means the probability density value for a normal distribution. Standard norm mean 0, standard deviation 1. What is the probability density value? And this is the F1 is cumulative density function. So when minus 1, what is the area under this? Okay, let's have a look at the normal distribution. So let's first visualize the PDF and the CDF for normally distributed random variable. So probability density function for continuous variable, while probability mass function is for discrete variable. So we're installing some packages if you haven't done so. So we're saying that mu equal to 0, standard deviation 1. So it is a standard norm with 0 mean univariance. So we are creating an x variable. So you can ignore at this one at the moment. So we are creating a few values. So the purpose is to show you the plot. Just show you the plot. You don't need to worry about the complex visualization scripts. So what you need to focus on here is look at these two curves. One is the probability density function for a normal distribution. Why do you know it's normal distribution? It's a 0 mean univariance. So it's a standard norm distribution called Z distribution. Then cumulative density function are also overlaid on here. So these are cumulative. So it starts from 0 till 100%. That's the maximum. While for the probability density function, it's showing there. When the x equal to 0, the probability density value is how much? It's shown here. 0.2419. 0.2419. 2419. Okay, so next is, let's look at x equal to 1, x to e to the 1. So we are going to calculate this F1. F1 is D norm probability density function 1. D norm x equal to 1, mean 0, standard deviation 1. Then if you use denorm 1, 0, 1, you get the same value as above. If you use just denorm 1, it is also the same as above. So the default distribution for denorm function is a 0 mean unit variance. So they're all the same. You get all the values. Then after that, we visualize on the on this chart. Okay, calculate the PDF value for x equal to 1. Well, let's have a look. So the x-axis is your x value. Then the y is for probability density function, it is the density value. So when x equals to 1, then your value for the blue curve is 0.24. 0.24, okay? Next, you will look at the cumulative density function. Cumulative density function, P naught 0.15. 0.15 when x equals to -1. Then your red curve, the red CDF curve will give you 0.158. So let's visualize it. When x equal to -1, your cumulative density function will return you 0.159. And when x equal to -1, your blue curve, which is your density function, density value will be 0.242. It will be same as x equal to 1 because it is symmetric. It is symmetric. Next, visualize and understand the PDF and the CDF relationship when x equals to -1. So let's understand their relationship. So when we have x equal to -1 and the probability density function will give you a value of 0.242. Remember, right? Recall that this is not a probability value, right? It is the density value. The probability, cumulative probability for x equal or less to -1 is, now say less or equal, it is area under the curve here. Area under the curve here, up to here. So the area highlighted in this light blue area, the value is 0.159. So the red curves, this dot 0.159, the value is equal to the sides of the highlighted blue area. Okay, it's equal to the sides. Okay, when your x is moving from -1 approaching 0, you will observe this blue area to get larger and larger and larger and larger. So when you are approaching 0 equal to 0, the area under the blue curve to the left of this line will be how much? Will be 0.5, right? So the total area under this blue curve is 1. Now I move x equals to 0. So the area under the curve to the left of this line is 0.5. 0.5. So you also know when x equal to 0, your cumulative distribution function will return you a value of 0.5. All right, return your value of 0.5. Okay, right. So that's the relation. When your x is moving there, x equal to 1, you'll have more area under the curve here. Then your cumulative density function will return you a probability value, which is even higher at this area. Okay, at this value. When your x is approaching the positive infinite, that means the total area on the curve will be counted, which is equal to 1. And your cumulative density function, will be also approaching 1, right? Approaching 1. Okay, good. Okay, so we have a good understanding of the relationship between CDF and PDF. The one thing very important is for the PDF value, it is not a probability value. Instead, the area under the blue curve to the left of this dotted vertical line is the probability. And it can be seen on the cumulative density function when x equal to 1. And the cumulative density function is the one. Is the P norm. Is the P norm. P norm minus 1 is the CD. And D norm -1 is your probability density function. Okay. Okay. Now, so next we are looking at the continuous uniform distribution. Continuous uniform distribution. Now here, this example, so X is a uniform distributed over 0 to 10, 0 to 10, this range. Calculate the probability that X lesser than 3, B, X greater than 7, and the X in between 1 and 6, okay? So the uniform distribution, So this is the uniform distribution. So DPQR, as usual, X minimum value, maximum value, and so on. So in our example, we're saying that X equals to P uniform is Q equals to 3. Minimum is 0, maximum is 10. So this is the value for CDF now. Yeah, P uniform is for the P uniform gives the cumulative density function, so CDF function. So this is the CDF function. So it gives you 0.3. Then if you use D uniform, so this is a probability density value. So this is not a probability value. Now, R random uniform, draw 30 values from a random, to draw 30 random numbers from the uniform distribution with a minimum equal to 0, maximum equal to 10. So they'll give you 30 numbers. 30 numbers, these are randomly drawn. Okay, so this is a helper function. So now it's asking, X is uniformly distributed over 0 to 10. Calculate the probability AX equal or less to 3. So let's look at that. X equal to 3. Highlight the area. So X is here. The total area under the curve is 1. So this range is 10 times 0.1. So that is area equals to exactly 1%. So now it's saying that X less or equal to 3. So this is the area under the curve here. And what is the size of the area under the curve? It is here. It is here. 3 times 0.1 is actually 0.3. So the area size is 0.3, and 0.3 is 30% of the probability. So next, X greater than 7. Let's have a look at X greater than 7. So X greater than 7 is here from 7 to 10. So that's the area. So 1, 2, 3, 3 times 0.1 is also 0.3. Right. Then for the C in between 1 and 6, let's have a look. In between 1 and 6, what is the probability there? You can also calculate. It is actually 1, 2, 3, 4, 5. 6 minus 1, 5 times 0.1 is 50%. 50%, okay? Then there'll be some exercise for continuous variables, P, D, and a helper function. Okay, so we have covered the demo part. Now next we are moving to the tutorial, okay, to the tutorial questions. So week 3, discrete and continuous random variable. So X follows a Bernoulli random variable with P equal to 0.3. Describe the small fx probability, density, or mass function. This is a probability mass function because it is a Bernoulli random variable. It is a discrete random variable. Fx is a cumulative density function for Bernoulli random variable. And therefore, okay, how do we do that? So we now switch to the AB1202 tutorial R solution 3.R. Okay, so let's have a look at the first tutorial question. Bernoulli random variable analysis. Fx probability mass function, and the probability mass function Fx equals to P if x equal to 1, 1 minus P if x equal to 0, and otherwise. Okay, now for cumulative distribution function, Fx equal to 0 when x lesser than 0. Now Fx is 1 minus P for any value in between 0 and 1, and Fx equal to 1 when x greater than 1. So you have a look at the solution. So F0 is 0.7, F1 is 0.3, and Fx equal to 0 in elsewhere. Okay. Then for the cumulative CDF, x lesser than 0 is 0. X in between 0 to 1 is 0.7. And Fx equal to 1, then it will be greater than 1, then Fx equal to 1. Let's have a look. Let's visualize it. Okay, right. 0.3, X follow a Bernoulli random variable. It has an assumption here, right? X equal to 1, then your probability is provided to you is 0.3. 0.3 is when x equals to 1. When x is equal to 0, the probability is 1 minus 0.3. So it's 0.7. Okay, so small f x equal to 0, it is 0.7. So when x equal to 1, your probability is 0.3. Okay, that's the one. Blue and red. Okay. Then question 2. Question 2. Suppose the distribution function x is given by this. This is the CDF. CDF, right? Cumulative density, cumulative probability function. X less than 0, 0. Between 0 and 1, 1/3. 1 to 100, blah, blah. What is a probability mass function of x? So question 2 is telling you, okay, cumulative one is this, then derive the probability mass function fx is, small fx is the bigger fx minus 1. Okay, so define the cumulative distribution function. We'll just have a look, visualize it. Okay, so this is the cumulative density function of x. Lesser than 0, 0. In between 0 to 1, it says 1/3. In between 0 to 1 is 1/3. Greater than 1, it is 1. It is 1, right? So when x equals to 1, it is 1 minus 1/3. So it is 2/3. Okay, you can calculate f1 is 2/3. f0 is 1/3. f0 is 1/3. 1/3 minus 0, then f1 is 1 minus 1/3. Then define and visualize the PMF. Okay, so this is the PMF. Because the question asks what is the probability mass function of PMF x. So that's the one. That's the one. So when x equals to 0, the value is 1/3. When x equals to 1, the probability is 2/3. Then for the rest of x, the value is 0. Okay, so that's the probability mass function for question 2. Question 3. What is question 3? Question 3. Suppose a random variable has a discrete distribution with the following PMF. Now, probability mass function, so discrete value. So it says for x equals to 1 to 5, then the fx is cx. X equal to 1, it is c times 1. X equals 2, then it's 2c. X equal to 3, then it's 3c, 4c, 5c, till 5c. So 1c, 2c, 3c, 4c, till 5c. Then all of them add together must be 1. Must be 1, right? So that means 1c, 2c, 3c, 4c, 5c. You add them together, it should be 1. So c times 1 plus 2 plus 3 plus 4 plus 5 is 1. So c equals to 1/15. 1/15. So that's the 1/15. So the constant c for PMF is 0.06666. Look at the c value. Question 4, binomial distribution. Suppose a coin have a probability 0.7 of coming up heads. Is tossed 3 times. Let x denote the number of heads that appear in the 3 tosses. What is the distribution we can use to represent x, determine the PMF, determine the CDF? Okay. So we analyze it. So number of tosses, we do 3 rounds of experiment. 3 rounds of experiment. The probability of head is 0.7. So this is not a fair coin, right? So if it's a fair coin, it should be 0.5. This is not a fair coin. The distribution of x binomial is binomial with parameters n equal to 3 and probability of 0.7. Bernoulli is you do only once. Binary outcome, but only do one experiment. Binomial is a repeated Bernoulli experiment. So the second one is a PMF of x. A possible outcome. Let's have a look. What is x? X is -2, -1, 0, 1, 2, 3, 4, 5. The number of heads, right? So we toss it for 3 times. 3 times. How many heads is possible? So that's just the x value for visualization purpose. PMF is d by norm. D by norm. Because that is the probability mass function, right? D by norm is the probability mass function, and the P by norm is the probability or cumulative density function. So it give x can be from where? From many heads. X equals to say what is the probability of having having two heads, let's say, sides. Size equals to n, so basically it's equal to 3, right? So here our b is p equals to 0.7, so we just do it. Example. So x equals to 2 is this value, 1, 2, 3, 4. So you have a chance of being 0. Then you do it again, 3, 4, 5, 6. So 0 heads, 1 has probability, 2 has probability, 3 has probability, 4 has probability, 5 has, 6 has. Why 4, 5, 6 are all 0? It's because you only do 3 times. So out of these 3 times, if all are heads, the maximum you can get is 3 heads. So if you get 4 heads, 5 heads, 6 heads, it's impossible. It's quite impossible, right? Then what about negative? Negative 1, negative 2, minus 1, minus 2, minus 2, 0, minus 1, 0. Because it's impossible to get a negative number of heads. The minimum you should start is 0. So total 3 times, they give all the tail. That's so 0. So here is just for display purpose. For display purpose, we plot it. So this is 1. So from 0, 1, 2, 3, 4, 5, there will be all 0. So 0, 1, 2, 3. That's the PMF of binomial distribution of 3 pulses. Okay, they also asked the second one is, third one is determine the CDF of X. CDF. CDF is you use the P norm, P norm, P by norm, P by norm, P by norm, X again. In fact, I just change everything here. I just copy it here, P by norm. Instead of D, P, but this time you should not use X. You should use P. Okay, negative 2 should be 0, 0. Start to increase, add more, and more, and more, till 3, you get 100%. Then 4, 5, 6, you continue to be 1. So it's non-decreasing, non-decreasing. It's always increasing. It's impossible to decrease. So CDF, so we're showing it. Now let's plot the CDF. This is a PMF. This is corresponding CDF. PMF, CDF. PMF, CDF. Okay. Non-decreasing. So getting higher and higher than up to 100%. 100%. So that is Q4, right? Then we look at Q5. Customer who purchase a computer from a store are known to have a probability of 0.01 to return the computer for a refund. What is the probability that among 10 random customers, at least one of them will return the computer? So we'll look at that one by one. Question 5, return the computer. Probability at least one return among 10 customers. So because they are say at least one is 1 minus 0 return. Okay, so that means at least one. That at least one of them return. So if you know 0% return, what is the probability of 0% return? It is this. This is the 0% that will return. Your return. So D naught. zero return, size equals to 10, and the probability is 0.01, zero return. Zero return is this amount. Okay. So 1 minus this zero return is a probability of at least one return. Okay, one return. Zero, at least one return, 0.09. So about 10%, about 10% chance. Okay, 10% chance. Majority is 90% chance is no zero return. 90% chance is zero return. So at least one return is 1 minus 0.9, so around 10%. Okay. Then the expected return. On average, how many computers are expected to be returned from 1,000 customer? 1,000 customer. The return rate is 0.1. Then the expected return will be 1,000 times 0.01. So it's about 10. Okay. Next, assume X follow a binomial distribution. Calculate probably X equal 10 for 1,000 customer. Assume it is follow a binomial distribution. Follow binomial distribution. Binomial is return, X equal to 10. So that means 10 return and among 1,000 customer with a probability of 0.01. Display. It is 0.1257. 0.1257. So we need to start to use the R code. Okay, we are starting to use the R code because X equal to 0. X equal to 10, exactly 10. So that's why we're using a probability mass function. Okay, probability mass function. X equal to 10 because they want you to calculate X equal to 10. Exactly 10 returns for 1,000 customer. Okay. Then next they say, assume it follows a Poisson distribution, X equal to 10. So now lambda is the average occurrence rate. Lambda, what is the value of lambda? Based on B, we know that the average occurrence is 10 returns over 1,000 customer. 10 returns over 1,000 customer. Okay, 10 returns over 1,000 customer. Then now we calculate the return rate. For the Poisson distribution, it is approximately 0.125. So it is very close to using a binomial distribution. Okay, it's very close now. Lambda. Average occurrence rate. So there are some calculations that you need to do for binomial distribution. Yeah, size is 1,000 customer, then number of returns is 10, and the probability is 0.01. While for the Poisson distribution, you need to know the lambda. Lambda is the average occurrence rate. Then we get this value from the previous few questions. 10. So question 6. A call center receives an average of 5 customer complaints per hour. Assuming the call arrives follow a Poisson distribution, what is the probability that the call center will receive 3 or fewer complaints? So when you see 3 or fewer, that means it is X is possible to be a range. So you should use a CDF function. And the next is what is the probability the call center will receive 5 complaints in the next hour? Then this is the PMF density, probability mass function. So Px less or equal to 3, what is the probability? 5 customer complaints per hour. So now I calculate hour rate. Average complaint per hour, lambda equals to 5. For A, P poison. P is a CDF because we are having 3 or less. 3 equal to 3 or less than 3. So we need to use POS. Lambda equal to lambda. Then we display. The cumulative density function when x equal to 3 is 0.26. Then what about exactly x equal to 3? Now, say PR x equal to 3. How do we calculate? You calculate by this. DPO, density function or mass function. 3 lambda equal to. So cumulative distribution function's value will definitely be higher than x equal to 3 because they also, the CDF contains x equals to 2, x equal to 1, and x equal to 0 as well. 3, 2, 1, 0. 3, 2, 1, 0. You add them together. You add this 3, 2, 1, 0 together. 3, 2, 1, 0 together. It should be the 0.26. We can do a quick check. Do a quick check. We just add. Zero 0.2650. We'll have a look at the previous one. So they are the same, right? They are the same. So you add them together. 0, 1, 2, 3. Next is Px equal to 5. Now, the 5 lambda equal to 5, then you have the probability of about 17.5%. 17.5%. Then we look at question 7. A florist makes delivery between 1 p.m. to 5 p.m. daily. They only deliver in the afternoon. Assume delivery time follows the continuous uniform distribution. Who use P uniform in R? P uniform is a CDF. Determine the percentage of delivery that are made after 4 p.m. After 4 p.m., including 4, 4.5, 4.6, 4.7, if possible, until 5. And determine the percentage of delivery between 2 p.m. to 3 p.m. So both of them, you need to use the P uniform. So it's not saying that exact 2 p.m. And it's impossible to know that exact 2 p.m. how many delivery will be there. The probability is actually 0 because this is a continuous random variable. For any given x, the probability will be 0. But the probability density value is not 0. It's not. Okay, 7. We'll kind of look at 7. The florist, the first question after 4 p.m. So minimum time 1, maximum time 5 p.m. So let's have a look at the PDF. Probability of delivery after 4. Let's just visualize it. Just visualize it. So from 1 p.m. to 5 p.m., right? Then for 1 p.m. to 5 p.m., the density value will be 0.25. How do you calculate it? So you find 1, 2, 3, 4. There is actually 4, right? 4 units. 4 need to time a probability density value so that the area under this curve will be 1. So your 4 times 0.25, the area under this blue line, the curve will be 1, so 100%. That's how these 0.25 density value are determined. Let me ask you, let's say, what is the probability for a parcel or the flower to be delivered exactly at 3 p.m.? The probability will be 0. Probability will be 0. But the probability density value will be 0.25. Right? Now, probably after 4 p.m. is here, right? It's here. So between 4 to 5, this area on the curve is 0.25. We can visually examine. Visually examine. And the second one is probably between 2 p.m. and 3 p.m. So just look at that, you will know. Between 2 p.m. and 3 p.m. That area on the curve is 0.25 as well. Okay. You can also calculate how do you get these between 2 to 3, right? So P uniform, then you tab quantile equal to 3, then minimum is 0. No, minimum is 1 or 1 p.m. Maximum is 5 p.m. So these are the area to the left of 3. Then you need to use this one to minus the area to the left of 2. This is 2. Then 0.5 there. Then you minus it. You get 0.25. So yeah, that's it. The area from 1 to 3 is 0.5 minus the area from 1 to 2, 0.5. So 0.5 minus 0.25 is 0.25. Okay, 0.25. Question 8. Then let's look at question 8. Z follows standard norm distribution. Give me one moment. Okay, we are looking at now question 8. So Z follows a standard norm distribution. Show graphically the probability between -2 to 1. So standard norm, 0 mean unit variance, unit standard deviation. So from here, annotate the area between where this one, this one, draw it. Okay, draw it. -2 to 1. This area. So basically it's this area. Hand drawing. Ugly hand drawing. Okay. So this. Clear. Then calculate the probability using RP norm, R norm, P norm, blah, blah, blah. Used to create vectors, namely. Okay. So that's the last one. So let's see how we use R to implement it. Question 8. Show graphically probability. Okay, so we're creating a x-axis, and the norm is the probability density value for the sequence. So just plot it. Okay, so here is the standard norm. -2 to 1. So the area on the curve. Okay, that's area. That area on the curve will be greater than 1 or lesser than 1. That will be definitely lesser than 1, right? The total area on the curve is 100%. And since we are not covering all of them, so the area in blue color under the curve will be lesser than 1. The second one, -1 to 3. -1 to 3, the probability is 0.84, around 0.84. 3. So P norm 3 are the area and the curve to the left of x equal to 3, z equal to 3. Okay, then minus the area to the left of z equal to -1, then you get this area from -1 to 3. -1 to 3 will be this area. Okay. Put it again. Okay, so say -1 to 3. Look at the second question, which is -1 to 3. This one. So annotate 3 is here, it's here, -1 is here. So the area is here. Area is here. Okay, so use the area to the 3 minus this area, then you get the remaining of this area. Clear our drawing. Fz for specific value. So this C is asking you for probability density value. So it's a small f, right? Probability density value. Now minus 0.1, 0, and 0.5. So they're asking for density value. So I'm just asking you for density value. So these are the density value. But the probability of x equal to minus 0.1 is 0. Okay, so the norm is giving you the probability density value, but not the probability. Optional for below. Yeah, optional for below. Or let me pause. Okay, then below is for optional ones. Optional one is to print all the Z values and the corresponding probability density value. Then the last one, scatter plot for Z and FZ. It says we use a sequence -3 to +3 by 0.1. So let's have a look. What is X? X is -3.0, -2.9, 2.8, and so on. So use blah blah by create a vector, namely, okay. So this is X. You actually can use the helper function SEQ to run it. Have a helper function SEQ. They teach you how to use it. So SEQ from, to, by. Okay, that's it. You can scroll down to look at some examples. There will be the examples here. So run examples. 1 to length 11 R norm, effective R norm, blah, blah, blah. 1 to 9 by 2 by pi, and so on. So this is using this. You can try this, copy, paste. They're showing by 0.05, 0.05 till 5.125. Okay, so we're using that method. Scatter plot X is quite a number of values. So fx d norm x, d norm x. Then that's the probability density value for each of these x value. So you assign it to a fx variable. Then next is to plot, give the x value and y value, x value and y value. This is the one that we expect you to plot. So this kind of straightforward plot you should be able to generate. Okay. Okay, so that's the end of this tutorial, and do remember to form your group by end of week 3, and make sure every one of you is enrolled in the NTU Learn system. Okay, then I will see you in the following week. Have fun, enjoy your Chinese New Year. Bye-bye.